pre-compute the chromatic number of every graph we use in advance, and we're giving the subjects exactly the chromatic number or number of colors. So we're not allowing any slack here. They actually have to find a proper minimum coloring of the graph. And you can see that this is, you can already see that this, in principle, this is going to be quite challenging, right? Because here you have this vertex number 2 here, whose degree is somewhere in the teens. So the likely experience of this subject is going to be very soon into the experiment, all 4 of the available colors are used in that neighborhood. And that subject has no real choice but to choose which subset of neighbors to conflict with, and then perhaps occasionally change that subset, okay? And so this is sped up a little bit, maybe by a factor of 2 compared to real time. But you know, what happens is people pick colors, they enter the experiments, they're seeing what their neighbors are colored, and you can see that indeed this vertex has no choice but to conflict with some subset of its neighbors. And you see the conflicts are kind of moving around. In general, you know, what needs to happen here, if I sort of, you know, project onto the subjects, which is of course always a dicey thing to do because they can play however they want to. But what kind of needs to happen is the conflicts need to propagate from higher degree vertices to vertices like this one, which is a degree 3 vertex in a 4-colorable graph. This is what you might call a fixer, who can resolve any conflict that arrives at it, okay? And so here, in far, far less than the allotted time, we actually have found a proper coloring of this network. And I would hazard to guess that even though this is an MIT audience, if when you came in the door, you had been handed this network and 4 colored pencils, and I asked you to, by hand, color this network, I would dare say that I would doubt that any of you would have found a proper 4 coloring